Yeah, let's look at the electrons in a finite quantum well. So just now we have a quantum well which is infinitely deep. So now we look at a case that V naught is finite. So this means that the barrier height at the two sides is finite, right? So in this case, of course, we still start from a Schrodinger equation, which is given by this. So we have this kinetic energy operator, which is part of the Hamiltonian. And then the other part of the Hamiltonian basically is potential energy. And since potential energy is a constant, so we can move it from left-hand side to right-hand side. And of course, the sign will change from positive to negative. Okay, so this potential energy is zero inside this well. And then outside the well is given by V naught instead of infinity. So now, since V is finite, so electron wave function now is non-zero in both barriers. So one to the left and the other at the right. So we had to solve this Schrodinger equation by separation of variable technique. So we can write this wave function as a product of three functions, and then each of them is just dependent on single independent variable. Okay. Again, since there's no confinement in y and the x direction, so electrons can move freely in these two directions. And then the wave function basically is the same. We still have the wave function of a free electron, right? So then you have and the wave vector in the y direction is ky, and the wave vector in z direction is kz. Right, and then in x direction, and then we have the confinement, though the potential barrier now is finite. So now inside the well region, so the Schrodinger equation will be like this, and then since V is zero, right, and then outside to the well region, so basically the two barrier region, and then you can see that and the potential barrier now is V naught, right? So inside the well region, and so we still have this standing wave as a general solution. But outside the well region, so we have two exponential decay wave. So one is for the left region, so x is negative and alpha is positive. So that's the reason why if you write in this form, you have a exponentially decay wave. And then for x, which is greater than L/2, basically in the right barrel region, and they have e to the power minus alpha x. Again, alpha is positive since the e is more than V naught, right? So that's why you have a decay wave. And then kx again is the wave vector of electrons inside the potential barrier. Since V naught is zero, so that's the reason why we have this form. Okay, so now if you apply boundary conditions at x equals minus L/2 and then positive L/2, right? And then so again, you have two boundary conditions. The one is the wave function is continuous. The other one is that the first order derivative of wave function is continuous, right? And then we'll not repeat this again, but if you're interested, you can submit this, substitute this wave function, apply the boundary condition to these three wave functions, and then you should be able to get this equation. Okay, so in this equation, we have the product left-hand side, and we have the product of two terms. So one is this one, and the other is one, and then the product is zero. All right. So now, so previously, and to solve this, and you have two cases. So in the first case, you can assume that so this term is zero, right? And so basically, you can rearrange this, and then you get alpha, which is equal to this, right? And then the other case is that you let this term be zero, and of course, get alpha as a function of kx again. So if you look at this two, right, and then you compare with this one, you can see that So alpha basically is a function, and so you look at this one, sorry, alpha is a function of kx, right? And then alpha here is also alpha is a function, of a kx, right? So remember what we are looking for. We are looking for the dispersion, right? The dispersion. This means that at E as a function of kx. So if we look at this one itself, right? So alpha. So you can see that alpha is a function of E, right? So alpha is a function of E. And so if we can combine this one with this one, this means that alpha as a function of kx. So we should be able, if we remove alpha, eliminate alpha from this equation and this equation, and then we should be able to find out E as a function of kx, right? But it's difficult to solve this numerically. So that's the reason why we can only solve this using the graphic method. So then we have two curves. So one is this one can open from this one, and the other one you can open from here, since both are two variables, alpha kx and alpha kx. And then similarly, we can combine this one with this one, and we have another set of equations, another set of solutions by solving these two equations graphically. So again, alpha as function of x and alpha of the function kx, right? So now this is what we have. You can see that alpha is a function of kx, okay? So now we have, we look at the first situation. The common equation is, the common equation basically is given by this one, all right? So this one is from, this equation. That's a common one, right? And then the other two are two separate solutions. So separate set of solution. One is from the intersection of this curve, right, with the curves which is defined by this one. So that this one basically is let me see, the second one, this one, right? So look at the second one first. So the second one basically all these blue curves, all right? And then of course another set of equation basically is defined by all these dotted curves, right? So now for at each intersection, we then look at this blue curve, the intersection, the intersection between this blue curve, the blue curves, and then this circular curve, and then at each intersection point, and then you have a corresponding value of kx. So you have kxy, kx2, and kx3, right? So once you have a kx, and then you substitute in, so this is basically, remember, you go back to this one, right? So once you know kx, and then substitute in, you can get a E, right? That is the energy with EX. So that's why I have EXN, which you can by h squared kx n squared divided by 2m. So n equals 1, 2, 3, and just continue, right? For example, if n is 1, you get a kx1, that basically is this point, right? And similarly, you can solve the other two equations, and then so you have so the kx2. So this kx2 basically is from the second group of equations, second pair of equations, right? So that's why kr2. And after that, you have kx3 and then kx4, right? So from here, you get this one. Okay, now, and that's how you can solve it. So next, we look at this penetration depth. So this means that since this V naught is finite, right? So that's the reason why now the wave function inside the two barriers is non-zero, unlike the case that when V is infinitely large. Okay, so when V is infinitely, V not infinitely large, when V not infinitely large in the previous case, and then so there's no electron here, no electron here. This means the wave function for electron must be zero inside the two barriers. But now you can see the finite, right? So how far this wave function can penetrate into this barrier region? So that is determined by this alpha, right? For example, if you look at this case, it's determined by this alpha. Okay, so and so 1/alpha is the penetration depth. So what does this mean? So when you propagate at a distance of 1/alpha, and then the wave function will decay to decay by factor of e to the power -1. So that's called decay length, right? And then if we use so since alpha is given by this one, right? In the previous slide, we already defined this one. And we can roughly estimate. So what's 1/alpha? Basically, is a penetration depth. So 1/alpha, so you get from here. So H-Planck constant. So m, you can use the free electron mass, right? And then V naught minus E. So we just give here. So substitute this Planck constant and then free electron mass into this equation. And you get 0.195 divided by rho square V naught minus E. So when V naught and E are in unit of EV, and then if you use this equation, calculate, and then delta will have a unit of nanometer. Okay, so suppose this V naught minus E is 1 electron volt. This means the barrier height is 1 electron volt, and then you substitute in, you find out the penetration depth basically 0.195 nanometer. Right, this is from a Schrodinger equation. And so why you have this penetration depth? Actually, there's another very simple way to look at this in quantum mechanics. That's called uncertainty principle. Okay, in quantum mechanics, actually for any wave, this is the same. So we have two forms of uncertainty principle. So one is delta x, delta p, the product of these two, and is greater than h/2. And the other one, so we're not using here, but actually it's very simple. It's delta t, which is uncertainty time domain, multiplied by delta E, which is uncertainty energy. So the product must also be greater than or equal to h/2. That's another one. Okay, so now we just focus on this one first. And in fact, for any wave, and you have this kind of relationship. Okay, this actually is not so difficult to understand, and this actually due to the fact that if you want to define any wave, right? And so, for example, maybe you just look at this. Okay, for example, if you want to define a wave, say one-dimensional wave in free space. So basically, if you don't confine it, and then you can define a very good, say for example, sinusoidal wave, right? So of course, if you want to confine it, and then eventually, and then you will get so wave packet, right? Say for example, if now you want to confine it to within, say for example, this region, right? And then basically the wave becomes smaller and smaller, right? And then after that, so this means that you only have a wave or something that this one, right? After that you confine it again, and then you get, say for example, something like this one. So eventually you just go down, and how small can it be, right? So of course, if it's less than one wavelength, then of course it's hard to see that it's a wave, right? So this means that when you go down to you limit this one in spatial domain, right? So just like this, confined, right? So this means that so this delta x become smaller and smaller eventually. Okay, so if this happens, and then of course since this will become wave packet, right? So this means that we learned in the previous case, and then so this momentum, the momentum itself will spread, right? Will spread. So this is same as when we talk about a signal in the time domain, and then frequency domain. You have the same relationship, right? So eventually, so and this when delta x, right, become comparable to the wavelength, okay, and then so in this case, so your momentum. So remember, so your momentum basically is when is well defined. So the momentum basically is hk, right? So k basically is 2 pi over lambda, right? So so this means that in order for you to have this kind of well-defined momentum. Okay, and then you cannot limit this delta x. Okay, so if this is difficult for you to understand this, let's look at Fourier transform. So basically, this is what we are familiar with, right? So remember, in Fourier transform, and if you have a a wave, this actually I explained before. So in spatial domain, which is not unlimited, right? And so this is a time. And then in frequency domain, and then you have a well-defined single frequency, basically just 1 point, say for example here, right? So if this is a signal as a function of time, and then this is a Fourier transform, and then you just get 1 point. So basically, so this is a frequency, it's a f naught, right? That's a frequency. And then so, however, if you limit this, and then what happens that according to Fourier transform, and then you basically, if your original function is given by, is a Vt, right? You limit means that you multiply this one by another window function, which is called Vt. So this window function basically means that, so for example, if I limit this one into this, so this is still sinusoidal wave, but you limit this within this region, so which is L, right? So it means that out of this region, and then it's 0, and the inside region is still this one. So it means you just multiply this one by this. So maybe not 0, it's T naught. So it just the window function. And then in Fourier transform, you should know that the Fourier transform of this basically is this one convolve this window function, right? So this Fourier transform, it means that when the actual function in the time domain is a product of two functions. And then if you do the Fourier transform, the frequency spectrum will be a convolution of the two frequency spectrum. So if this is originally is a sine function, which is extended in the entire time domain, and then you just get 1 point, which is this one, right? However, convolve this. So this is just a rectangular function. Then the inside you can see is 1, outside is 0. So the Fourier transform of this, you know that is a sinc function, right? Sinc function. This means it's a sinc function, right? So sinc function, of course, has a certain width. The width is inversely proportional to the width of the window function in a time domain. That's why when this when this becomes small, when this decreases, and then of course this width will increase, right? So when you convolve this one, this sinc function with this point function, and then basically you get this one itself, right? So that's the reason why, and then it becomes wider. And then of course mathematically you can find out that the spreading in the f frequency domain and the spreading in the time domain, the product, and then it's a finite value. Okay, so this is the same as uncertainty principle. Anyway, this applies to all type of waves. So I hope you understand this. Okay, so let's go back to this, and then so basically we're talking about the product of delta x and then delta k. So remember, delta k is the spatial frequency, right? So spatial frequency, the spreading of spatial frequency in terms of spreading in the spatial domain, the product should be finite. But momentum is hk. So that's why if k change by delta k, and then momentum will change by h delta k, right? So that's the reason why eventually you have this kind of uncertainty principle. So now look at what happens for electrons near this boundary. Okay, so near this boundary, of course, if electrons inside here, you can see the energy here is 0, and then outside here, and then so energy would be V naught, right? So that's why there's an uncertainty of energy. So that means that so this in order not to mess up this one, so just use this. So it means that this is this kind of relationship. So the energy uncertainty for electron at the boundary will be given by delta E. So that delta E uncertainty of this will give you the same uncertainty in momentum. right? Just follow this one. So this means that the momentum uncertainty is simply given by, so this one multiplied by this one, it takes square root, right? And then, so what's the uncertainty of this delta E? So the uncertainty of delta E, so basically is given by this V naught. So if electron jump from here to here, of course, if this electron here, you have energy somewhere here instead of at 0, and then the difference basically is from here to here. So that basically is V naught minus E, that's the uncertainty, right? This means for any electron with energy E inside here, and then if you want to jump from here, then energy will change by this amount, right? So that amount basically will be converted to delta P, and then from an uncertain principle, you know that this electron cannot be fixed at this boundary. It must have uncertainty within this range. So that range is given by, from here you get H divided by 2 delta P. So delta P is one, so you get this one, right? So now I can see that this basically is similar to this one, right? So, and then the only factor of 2 is the difference, right? So that's a factor of 2. You can see that this uncertainty we're talking about, it just move, basically you can put to this direction or this direction, right? So if you just put into this direction, then roughly, so what you get is this one, right? Of course, even without this, it's still okay because the order is still stable, right? So that's why, so this basically is given by this. Sorry. So this basically is similar as this penetration taps. So basically gives the uncertainty, all right? So this uncertain principle is very, very important, okay? So in many cases, you don't need to do all these calculations. So roughly you will know from this uncertain principle, you can estimate, right, what's the uncertainty in another domain, right? Say for example, if you have any interaction in quantum mechanics, and it involves energy uncertainty of a certain value, and then this kind of process, right? This kind of process in the time domain, so basically you can estimate. So what's the duration of this kind of process in time domain? That basically is H over 2 divided by delta E, right? So in other words, if you have a process which is extremely fast, and then this means that it involves high energy because delta E is given by H over 2 divided by delta T, right? So in quantum mechanics, we can use this one, okay? Don't need to do all the detailed calculation. This is just estimation. This basically tell you, so roughly, what's the range of energy over time for a certain process, or if you have a wave, and then if you know the spreading in one domain, you should know the spreading in another domain, right? Because they are inversely proportional to each other, okay? So now, let's look at what happens if we try to confine electrons, and not just in an X direction, but we also try to, additionally, we try to confine electrons in Y direction as well. And then we only allow electron to move in Z direction. So in this case, we have one-dimensional confinement system, which is called quantum wire. Excuse me, because it looks like a wire instead of a well, right? In this case, again, in order to understand how electrons behave in a quantum wire, we have to start from a Schrodinger equation again. So again, we have this simple Schrodinger equation. We'll assume that this barrier is infinitely large. This means that electron can only move inside this wire and outside this wire, outside the wire, and then potential barrier is infinitely large, right? So in this case, electron can only move freely in Z direction, right? So that's why the general solution, you have, so Z direction, you have a plane wave, but X and Y direction, you have a standing wave, okay? So so there's a standing wave, of course, this coefficients in X and Y direction are different. And then we'll apply boundary conditions in both X and Y direction. So in the X direction, so what you have, this means when X is 0, and then this wave function must be 0 because you can't have electrons outside this on the wire. And then, so you get A1, which is 0, because when X is 0, so this is 0, so A1 is 0. And then when X is L, so the wave function is 0 again, so L is 0 again. And from there, you can get a K, KXL, which is M pi. So now we use NX instead of N because we have another one, we see NY, okay? Okay, and then we find that the kx is quantized, which is given by this. And similarly, and so you have the boundary conditions in y direction. So y is 0 or y is L, and then so this wave function must be 0. So from there you find that ky is also quantized, right? So L is the dimension of the wire in both x direction and the y direction. Okay. So now we can see that this kx ky quantized, and then we substitute in, and so we should get energy. So now we can see that the energy, and so so kz is able to change continuously because there's no confinement in z direction. But in x and y direction, you can see that kx is a wave number is quantized. Okay, and then we have two different indices. So one is for kx, the other one is for ky. Okay, so now if we try to sketch this energy level and also wave function in the quantum wire, you can see that it still looks very similar to that of a quantum well, but there's a difference. So the difference is that now these energy states, local energy levels, are specified by two integers instead of just one in the case of quantum well, right? So the smallest energy, the lowest energy will be specified as 1, 1. This means nx is 1 and y is 1, right? And then, so the next one is interesting that we have two combinations. So one combination is nx is 1 and y is 2, and the other one, nx 1, nx 2, but ny is 1. And they both have the same energy. You can look at this formula and for energy. And that's because that the dimension of the wire in the x direction and the y direction is the same. Of course, if they are not the same, and then they're not necessarily to be the same, right? The energy will be different. Okay, so so this is called degenerate state in quantum mechanics. Okay, because the energy is the same. Okay, and then if you look at the dispersion, so this means that the energy as a function of kz, because now kz is the only wave vector which is able to change continuously, and then we can look at the dispersion. So now you can see the dispersion is still still have a parabolic shape. That's because that is defined by this, right? This is similar to the quantum well case. So remember, in quantum well case, this is not kz, it's a k parallel. So this means that it's a wave vector in the zy plane, right? In quantum well case. But in quantum wire, so since we also have confinement in the y direction, you only have one direction, which is free for electron to move. That's the z direction. That's why I kz here, right? Now, we look at this dispersion. So this is for the first sub energy level. So you can see that, so this is a kz term, and then this is the kx and ky term. Since the kx and ky are equal to each other, which is put together. So since nx is 1 and y is 1, you know, we got this one. And the second one, so you have this, right? And so this 5 comes 2 squared plus 1. So 2 squared plus 1 or 2 squared plus 1. So you get both. That's why this is degenerate, right? You have two different states which have the same energy. And then you move up, the next energy state begin defined by 2, 2. So 2, 2, you only have one combination, right? So this is not degenerate, right? You only have one subband, right? And then this subband is energy defined by this, right? This is called EK dispersion. Okay. Now we try to confine electron further. So this means that we try to confine electron in z direction as well. So this means now we have a quantum box or quantum dot. So in this case, you can see that the electron cannot move in any of these directions because this energy barrier is still infinitely high. So this means the electron can only be confined inside this small volume, okay, which is a box. So again, we solve this Schrodinger equation, and then inside the box, and so basically this V is 0, right? And then outside the box, so V is infinitely large, and then so wave function must be 0. And then so we just again use this separation of variable method, and then you have three second-order differential equations. All right, and for electrons moving in all the three different directions. Then, so after that, you have a general solution. So it means that you have a standing wave in all the three directions due to this strong confinement. And after you apply the boundary conditions, so basically when L is 0, and then other function, wave function is 0, and then when x, y, z, when x, y, z are L, and then wave function is also 0, and then you get this. So I can A1, A2, A3 must be 0, right? And then after the B1, B2, B3 cannot be 0. So that's why we require that an XL and YL and an NZL as a multiple of pi, right? And then from there, you find that the KX, KY, KZ, and then all quantized. And then, of course, the energy is perfectly quantized. So you don't have any continuous variable here, right? So of course, in this case, the wave function became like this, which is normalized. And then if you sketch out, and this is what you have, right? This is just in one direction. And then of course, you can sketch in the other direction as well, right? So, but we don't have dispersion in this case because the electron cannot move. So that's why you don't have dispersion. Okay. So now, if we combine, and it's in the quantum box case, so since there's no dispersion, so we only need to calculate the energy at the different energy levels. And since the Kx, Ky, Kz are all quantized, and then we have a higher degeneracy in this case, right? Degeneracy. This means that some of the energy levels are degenerate as a higher degeneracy. This means that many different states, but they have the same energy. Of course, we do have energy levels which are non-degenerate. Right? So for example, now look at the first case, 111. So in the 111, and then this is non-degenerate, right? And then you have a next one. This is threefold degenerate. This means that you have three combinations, three different states, but they have the same energy, right? And then you move on to the next one. You have a 221, 212, so 1222. So this is the energy is 9 multiplied by this, and this is threefold degenerate. Right. Similarly, next one also threefold degenerate. Right. And then so then you reach to 222, and then in this non-degenerate. Right. And then above that, so you have another state which is six-fold degenerate, and then three-fold degenerate again. Right. So on and so forth. You just move on. Then you can try to figure out what's the degeneracy. Right. So now we try to put all this in the same picture. So you can see that for free electron, and then this is our EK dispersion. So remember, K is the magnitude of the wave vector. So basically, it's Kx squared plus Ky squared plus Kz squared, and then take a square root, right? And then electron is able to move freely in all different directions because there's no confinement. So that's the reason why we call free electron. So the energy as a function of K, you have this very simple expression. So this gives you this parabolic shape of a dispersion. So now you try to confine from one direction. You try to confine from X direction, but the electrons can still move freely in ZY direction. And then you have this, still have this parabolic dispersion, but this dispersion is only respect to the wave vector in the ZY plane, in which the electron can move freely. But in X direction, so this Kx is quantized. So that's the reason why you have this sub-energy bands, right, or sub-energy levels. Okay, and then you can see this dispersion is E as a function of K parallel, and then K parallel is a wave, the length of wave vector in the YZ plane, right? So now if you confine further from Y direction, and the electron can only move in Z direction, you have the case of a quantum wire. So for this quantum wire, if you look at this energy level and also wave function, and then more or less the same as the quantum well. Right? If you look at dispersion, the shape is also almost the same, but there's a difference. So what's the difference? So this dispersion is the relation between energy and then kz vector, right? So this kz and actually is a wave vector in the z direction, because this is the only direction which electron can move. And then the minimum of each subband now is specified by two integers. So we have two indices, right? So that's the reason why. And so you will have the concept of degeneracy. So this means that a certain energy band, for example, this one, is degenerate. This means that you have two states for the electron. Of course, the two states have different wave function, but the energy is the same, right? And then if you confine further from z direction, you have a perfect confinement. It's similar to electrons in the atom, right? So of course, in atom, you have a spherical environment in symmetry, but here we have a cubic symmetry, but the idea is the same. So basically, you can say that in this case, electron is completely confined, okay, in all three directions. And then you have a discrete anti-levels, and then of course there's no energy dispersion because the electron cannot move, right? So we have all these different situations. And this kind of quantum confinement are extremely important for optoelectronic devices. And most of the optoelectronic which you will learn in the second part, for example, light emitting diode, and then semiconductor lasers. So all of these rely on this two-dimensional quantum wire structure. Okay, and the quantum wire and the quantum dot are also very important, right? So quantum dot actually, and quantum dot is also used in many applications, right? Even in biomedical applications, right? So, but overall, now the most useful device so far is still the quantum wire. We call 2D system. Okay, 1D system is somehow theoretically it's increasing, but in most cases, and the 1D system is not very useful. So why this is the case is because that since electrons only move in one direction, and then you have some sort of instability, which we'll talk about later when we talk about dense of states, right? And of course, some materials, this is, for example, charge density waves, all of this. You can observe some interesting phenomena in 1D case, but in practical applications, it's not very useful so far. Okay, now next we have very important concept in solid physics, and of course for semiconductor it's also very important. Almost for any type of solid state material, right? Be it a metal, superconductor, and then ferromagnet. So the density of states plays a very, very important role, right? So, so what this? So I'll just give you a very simple idea about this. Okay. So this basically show you copper in real space in different shape, right? So this is just a simple block, and so this is something like a cylindrical shape. There's a wire, right? And so this is a block with many holes, and this is art, right? Copper-based art. But so all of this, okay, just try to imagine that inside is a copper. No matter how you shape it, right? You have many electrons inside this copper which can move freely. So this means that if you apply a driving force, electrical driving force, and then electrons will move, will drift. And actually, even you don't apply any driving force, electrons are moving very fast inside the copper. However, electrons are moving in all random directions. So that's the reason why there's no net current flowing inside the copper if you don't apply a driving force with a directionality, all right? So, all right. So this is in real space, but just now we use the word that electrons are moving randomly, right? So this means that if you want to count the number of electrons passing through a certain cross-section area inside this metal, the net flow of electrons is always zero. So that's the reason why I don't have the current, although electrons are going very fast. But that kind of concept, we can use a reciprocal space. So remember, when we talk about the lattice lattice, and then we have a lattice in the real space, right? And then I explained during that time that and the reciprocal space is extremely important. So because in reciprocal space, what happens that in real space, and then if you treat electron as a quantum mechanic phenomenon, right? And then electrons inside sorry, maybe I just need to use this whiteboard to explain first, and then come back to this one. It's easy for you to understand. All right. So so if you have a piece of copper, you see I have this shape. So inside you have so many electrons, right? Many electrons. And each electron is moving at a very fast speed in all different directions. So for example, if the velocity of the electron is given by VI for S electron. And then you can count. So if you try to find out what's the overall average velocity of this one, so it's from 1 to infinity, when this is always 0. So that's the reason why there's no net current, right? So this is, you basically treat the electron as a particle in classical physics, and you can try to do that. But remember, in quantum mechanics, electron is also a wave, right? So basically, so inside this, so you have all this wave with a different wavelengths, right? So each of this is just a wave, okay? And then if the wave, of course, and so we don't specify the position of the electron, right? So the wave is always given by wave vector k, right? So that means that each wave is just represented by wave vector kx. Okay? So in this case, so you can say that we can use this concept. This means that we have a reciprocal space kx, and then ky, and then kz. And then for each of these, it's just a point, right? Just one point in KZ coordinate system. We don't need to draw the wave because one point in this space, kx, ky, kz, is just one point, right? So all of this wave, so for example, you have a very long wavelength one. And then, for example, when this wavelength is very large, and basically it's here, right? Because remember, k is equals 2 pi over lambda. So when wavelength is very large, and the k is very small, so that's why it's 0. And then, of course, and then we have a shorter wavelength, and then it will increase. So later we'll show you that what's happening, that because electron is a formula. So, and then remember, k is related to energy as for free electron, right? You have so hk, which is the momentum square divided by 2m, that basically is the energy. So this means that for formula, electron will always try to fill up the states with the smallest energy first. So this means that electron will always try to fill up the states with smallest k first. So eventually, so after you use up the k, and then due to this square, this k square here, and there's a e here, so eventually end up with a spherical surface. So inside this spherical surface, and then every point is filled up. So this means that we have each point is just a point with different k. So different k means that a wave with different wavelengths, right? So, and then you can have all different shapes of the copper. So eventually, in real space, in k space, it's always a spherical shape. So it means that you have a copper, there's a block, you have a copper wire, and whatever. So in real space are different, but when it comes to reciprocal space, it's always just like this. Okay, so this is what you have, and this reciprocal concept is extremely powerful. Why? Because if you really want to calculate the current conduction in the real space, you need to count the contribution from every electron. But you have a huge number of electrons, so that's very inconvenient, right? But in reciprocal space, what happens that we don't need to count the electrons, the contribution from all the electrons, right? So what happens that when you apply a small driving force to this metal. This whole sphere, this whole sphere will just shift a little bit, in the in this K space, and then this shift, net shift, will contribute to current conduction. In other words, most of the electron inside this sphere will not contribute to electric conduction. Okay, and only those which have a very high K value and then stop at this surface. This is called Fermi surface. Later is going to you on this electron, the Fermi surface, which will contribute to electric conduction. Right. So I'll come back to this concept again. So this basically is this picture which I want to convey the message to you. So this means that in real space, your metal can have all these different shapes, but in reciprocal space, it's exactly the same for the same type of material. For example, if this is copper, and whatever shape you have in real space under measure, and then in reciprocal space, you only have this spherical shape. And the electron will start to fill up these states at the lowest energy first, and then eventually end up with the energy we call Fermi energy, right? And then because you use up all the electrons, you just stop here. And then when you talk about electric conduction, you don't need to look at electrons inside this sphere we call Fermi C, inside Fermi C. We only concentrate on electrons at the Fermi surface, which is very important, right? And how is this related to the density of states? Because you can see that on this surface, for free electron, okay, you have the same energy. If you have many electrons with the same energy at the same energy level, especially at the Fermi surface, so this will determine the property of material. Just try to imagine that if you have a huge number of electrons at the Fermi surface, right? And then when this Fermi surface just move a little bit, and then this will give you a huge effect. This is exactly the same as not exactly the same, but anyway, you can try to visualize the water in the ocean, right? You have a huge amount of water in the ocean. So when this ocean just shifted a little bit, right? You just try to imagine how much of the water will move, or what's the water flow, right? You have a huge water flow, right? When huge amount of water is flowing when this ocean is moving a little bit, right? So this means that this density of state we're talking about is number of electrons you have per unit volume in real space, per unit volume in real space, and then per unit energy interval in K space. So this is the density of state we're talking about. When this is very, very high, and then you have a lot of interesting phenomena will happen, in this material. If this is zero, it means that typically we're not interested in this kind of material because you don't have much carriers from the surface for you to play with. Okay. And now, in order to understand this Fermi level concept, so now we look at this. Try to figure out what's the volume. Okay. What's the volume occupied by each single state in the K space? In real space, you know that the volume occupied by a single electron, you can calculate from the concentration, right? So if your carrier concentration is given by N, and then the volume occupied by single electron, so roughly is given by 1 over N to the power of 1 over 3. Right? So that is roughly is the volume occupied by a single electron if the carrier concentration is N. And then in reciprocal space, we can also find a similar concept. This means that we should be able to find out what's the number of electrons which occupy a single electron state, right? So we should be able to find out what's the volume in K space occupied by this single state of electron. Okay. So now to do this, and we try to apply this periodic boundary condition. This is similar to the case that when we talk about the phonon, right, in lattice vibration. And then remember, we applied the periodic boundary condition, right? And so for electron, we can do the same. Although this looks like it's just some sort of mathematical trick, but actually is very, very useful. Okay. So now, if you have a free electron, this is basically let me turn on the laser pointer. So this is basically the Schrodinger equation for free electrons, right? Just now we talked about the quantum well, the quantum wire, and the quantum box. So now we look at the periodic boundary condition. This means that the wave function will repeat itself when you travel a distance of L in x direction, L in y direction, and L in z direction. This is to mimic the real situation in a crystal. Okay? So if this is the case, and then we still we just try to focus on free electron first. So electron can still move freely in space. The only difference that we require this wave function to be periodical. So this period is L. So that we can use this one to approximate the situation in real crystal, right? So if we do this, and then so this is basically the general solution for free electrons. So we have the plane wave, right? And then after that, we just apply this periodic boundary condition. And we do this, and you can try to do it by yourself, apply the periodic boundary condition to this, this, and this. Then we find that Kx, Ky, Kz are all quantized. So in this case, it's quantized in this form. So it's 2 pi over L. So L is the period, right? In x direction, y direction, and z direction. 2 pi over L, and then multiplied by nx, ny, and az. So nx, ny, and z are integer. Okay. So remember, each k represents a state of electron, right, in residual space. So now, so this means that the volume occupied by a single state, a single k, what we call k state, right, in k space, basically is given by 2 pi over L cubed. This means that when each of these changes by 1, right, here number 1, and then you get this is more volume. So it's a very important result. And so the L, so later you know that the absolute value of L doesn't matter. So this is just a mathematical trick. You can change L, you use whatever L you want to use, as long as it's large enough. Large enough means that it won't be too small, just comparable to that spacing we talk about later, right? So and then you can have freedom to choose L, but eventually the physical result is still the same. Okay, so and you only know that each k state in k space will occupy a volume of 2 pi over L cubed for 3D case. And then for 2D case, of course, would be 2 pi over L squared, that'll be area. And in 1D case, this is an interval. This is 2 pi over L. So this is something you need to remember. Okay? Then we can use this concept to derive this Fermi energy, Fermi wave vector, and the Fermi sphere, right? Okay, so now, so once with this, so now we can try to derive this density of states step by step, right? So the first thing we need to understand is that so once we know in 3D case, once we know that the volume occupied by a single k state is given by this one, and then each k state can be occupied by 2 electrons because the electron has a spin. So it means the electron has a spin up and spin down. Okay, so this means that the volume occupied by a single electron in k space is just half of this because you have 2 electrons, right? So each will occupy half of this. So once you know this, and then we just try to fill up this k space from the smallest energy first, right? So that's because that we know energy, because energy is given by, remember, so energy is given by, let me just see, okay. So since energy is given by this, right, it's the h squared divided by 2m, and then kx squared plus ky squared plus kz squared. And then for periodic case, we already derived that this kx, ky, they are quantized, right? So however, if we try to increase L, the quantized means that you can see that now each single K state will occupy and the volume we call 2 pi over L cube. And then one electron will occupy half of this, right? Then we just try to fill up this one from Kx, Ky, Kz, the smallest one first. And after gradually increase this. So when you increase this, remember, we have many equivalent K states with the same energy. That's because that E is given by this, right? So as long as this one is the same, and then although Kx, Ky, Kz can be different, and you have many different combinations, you know that, so if you let this be a constant, you have a spherical surface, right? So, so now, of course, look at this, looks like you have this kind of discrete or very rough, surface, but actually, when you let L approach infinity, and then this delta V K approach 0, so this means that, so this will become a infinitely small, right? So eventually, so after you use up all the electrons, right? Use all the electrons, and then you stop at a surface in K space. So this surface has a spherical shape. Why? Due to this ring shape. And then this surface can be very, very smooth because your material in real space, the periodicity you use can be very large. So that's the reason why you have something called Fermi sphere. Okay. So you have a spherical shape exactly because of this dispersion, right? E is proportional K square, this kind of dispersion. If you don't have this kind of dispersion, of course, you won't have a spherical shape. Okay. So the density of states at the Fermi level, this means that once you stop here, you have a Fermi surface, and the density of states at the Fermi surface plays an extremely important role in determining the property of the solids. Okay. Now, you can see that this is the concept we just talked about. So in real space, for your material can have all sort of different shapes. For example, you have this kind of cube, but in reciprocal space, you only have a spherical Fermi surface. So all the electrons will occupy the states below the Fermi surface at zero temperature. Okay, so and above this Fermi surface, they are all empty states. Okay, and then how to find out the size of the Fermi sphere? So we can do a very simple calculation. So the volume of the Fermi sphere basically is given by this one. And so Kf is called Fermi wave vector. This means that it's a radius of the Fermi sphere. And then for the volume, basically given by this one, right? And then this is related to energy. Kf is related to the energy of Fermi surface. So it's called EF. And then in this relationship, that's because that the E equals h squared K squared divided by 2m, right? Okay, so now, the total number of electrons contained in the Fermi sphere, that basically is, remember, we know the volume occupied by a single electron. So that's given by this one, right? That's a volume occupied by a single electron. And then this is total volume of the Fermi sphere in K space. So this must be the total number of electrons you have, right? And then the total number of electrons in real space. So this means that we can have two representations. So one is in real space, and one is in reciprocal space. And the number of electrons you have in the total space must be the same, right? Otherwise, it doesn't make sense, right? So the number of electrons in real space. So once you know the electron density, and then you just need to multiply the electron density by the volume. So volume is L cubed, right? And this two must be the same, right? So this is the reciprocal space representation, and this is from the real space representation. So the total must be the same, okay? So now you can see that why we explain that L is not important, because you can see L can be canceled out, right? So this L and this one can be canceled out because this is this L is at the denominator of this entire term, and then again is at the denominator of this one. So that's why it flip over and it cancel out. So once it cancels out, and then you can see that, okay, I just rewrite this one. So this is the number of electrons in real space, and this total number of electrons in reciprocal space, since they are equal to each other. And then we rearrange this equation. So we can see now this L cube cancels out, right? And then from here, you can find out Kf, so which is a Fermi wave vector size of the Fermi sphere, right? It's directly related to the carrier density in real space. So from this, you can calculate the Kf. So this Kf is basically now is given by this, right? And then once you know Kf, and then you can calculate, the wavelength. So this is a wave vector of electron at the Fermi surface. And then, so this is the wavelength at the Fermi surface, right? So now we can use copper as an example, and then to find out roughly, so what's the wavelength of electron at the Fermi surface. And then you realize that this actually is very, very small. Okay? So how to calculate copper? So we know the carrier density, electron density of copper is given by this one. You can find this from textbook. And suppose we have a piece of copper in the cubic shape with a size of 1 meter. Okay? You can use 1 centimeter, 1 millimeter, or 1 micron, or whatever, right? Doesn't matter. Okay? And then you substitute this one here, you can carry Kf, you can do by yourself, it's given by this value. Okay, so now if you look at the delta Kf, delta Kf basically is the change in one direction, right, in K space, if you by changing one state. So that's basically 2 pi or L. And 2 pi or L, remember delta Kf, right, is 2 pi or L. So 2 pi or L, so L is 1 meter, and then put in here, you can see that this is the value. And you compare this delta Kf with the Kf, you can see this is extremely small, right? So what does this mean? This means that actually the Fermi surface is extremely smooth. So that's why it's just like a sphere, right? Not like, initially we use a large volume occupied by 1 electron in K space. It looks like very rough, but actually not. It's very smooth. And then what's the wavelength of electron at the Fermi surface? So the wavelength of electron Fermi surface, you can see is extremely small, right? So it's 2 pi over Kf, and then for copper, it's 0.46 nanometer. So basically it's 4.6 angstrom. So this is something like a length scale of electrons in metal, okay? So this means that electron is a wave. Inside the copper, you have electrons with all different type of wavelengths, right? And those near the Fermi C will have a long wavelength. But these kind of electrons, it's just like water in the ocean. They won't contribute to electrical conduction, right? Just imagine if you have a large tide, maybe like a tsunami. Maybe tsunami can move this the water in the ocean, right? In a large to a large extent. But even that's the case, and then so water far from the surface or from the ocean surface are still don't contribute so much, right, to this water flow on the surface of the ocean. However, does this mean that electron inside the Fermi surface, deep at the Fermi C, we call Fermi C, deep at the Fermi C, is not useful at all? No, because without these electrons at the deep Fermi C, you won't have electrons at the Fermi surface. Why? Because electron is a formula. Electron must occupy the energy states with lower energy first, and then gradually when you move up, and then you have electrons at the Fermi surface, right? If electron concentration is very low, and then your Fermi surface, Fermi sphere will be very, very small, and then you have a very little number of electrons on the Fermi surface. Now, of course, this will not be a good electron conductor, right? So this means that the anti-support is extremely important. This is like, I don't know whether this energy is is appropriate or not. Just look at our human society, right? You have all these so-called high achievers, right? Like people who are leading large multinational companies. Of course, they contribute a lot to the society, right? The impact is huge, right? But remember, in all these MNC or multinational companies, and so you have so many people working very hard to support this organization, right? Without all these people, of course, you won't have people at the top, right? Right? But in terms of the impact, and then of course people see that the impact at the top is always much larger, right? Than those who are working, for example, at the different positions, right? So anyway, this might not be so appropriate, but anyway, just try to help you to understand this kind of situation. Okay? So this means that the electrons at the Fermi state is extremely important. So now I hope you understand roughly the difference between this real space representation and the reciprocal space. So reciprocal space means that we really focus on those who can make a huge impact. And then in real space, we really look at each electron, right? But the net result, the final result, the physical effect is the same. Okay? That's very important. Now, you can also try to find out the Fermi wavelengths of gold and aluminum. These are very good conductors. So, and end up that the wavelengths, Fermi wavelengths, so roughly within this range. So this is the reason why it's very difficult to observe quantum confinement effect of electrons in metal. So this means that you can easily realize quantum confinement in semiconductors, as you learn this in the second part, right? And also in this part. And that's because that the length scale of electrons in semiconductor is much larger than the length scale in the metal. So in the metal, because you can see that the Fermi wavelengths, so we are focused on electrons at the Fermi surface, the Fermi wavelength is very small. So therefore, in order to realize any quantum confinement effect, you must make your metal as small as or comparable to this Fermi wavelengths. So that's the reason why people are trying to do this kind of experiments. So what this, they have basically two pieces of metal, for example. So this is a copper, it's another piece of copper. And actually, the gold is much easier. You go to do it because gold cannot be oxidized so easily. For example, this is a gold, another piece of gold. And then you have a very, very small contact here. So this contact is almost comparable to this Fermi wavelengths. So when this happens, so if you try to measure like electrical conductance between this electrode and this electrode, and actually you can see that the conductance itself is quantized. So this means that electrons are wave, and then when wave is confined, and you have different modes. So each mode is corresponding to a certain conductance. So eventually you can really count, the electrons which passing through this. Even you get a quantized conductance, right? So it's just like a water pipe here, and inside this water pipe, you have many narrow pipes. So each pipe is contributing to a certain amount of water flow, and then so you can fill up this pipe one by one, and then you see that the water flow itself also quantized in a certain sense, right? Okay, now we can try to derive the density of states for electrons in different dimensions. So first, since at the Fermi surface, and so this is what we just derived because the Fermi energy is given by h squared kf squared divided by 2m, and the kf is proportional to, so not proportional, it's really to the carrier concentration, right? So the carrier density in real space. So carrier density in real space is the total number of electrons divided by the volume. Okay, so this is the n we just used. Okay, and then if we, this is a Fermi surface. If we look at any energy which is between 0 and then Fermi surface, so we just call arbitrary energy E. And then of course this within this energy E, and then it will define this smaller spherical surface, right? And then within this spherical surface, so number of electrons we have, which is called N. So it's different from the total number of electrons, just N. So within this small, this green region, okay? And of course, and so this wave vector, so now it's given by this one. So this wave vector now is related to, this one instead of, this N naught, right? So, and then from here you can see that, so K and then N are related to each other because so this would be, the volume basically is still the same of the volume of the real space, right? So when we try to differentiate this one, okay, anyway, we just rearrange this a little bit, and I can say N is a function of E, right? So this N and this E, right? So N is a function of E. So now we differentiate this one from two sides with respect to E, and then we'll get, so dNdE, so that dNdE, so this V is the volume in real space. We just bring it over, so you have 1 over E here, right? And then I just rearrange this part a little bit different, this one, and then you get the root square E, because it differentiates this one with respect to E. So this is 3 over 2, right? Yeah, root square E. And then, so all this constant here, just rearrange it. So this is what you have, okay? So now, okay, so this is what you have. Now, this is a density of states. So what this, you can see that this is a number, right? So number of K states is N, right? So this N, sorry, number of electrons. Okay. So this is basically is number of electrons, okay, per unit volume in real space, and then per unit energy interval in energy space. So this whole thing is called density of states, right? So I repeat again, number of electrons per unit volume in real space, and then per unit energy interval in energy space. So this is called density of state for dE, which is given by this. Okay, so this is a proportional to root square E, right? So this is a if we can, okay, so anyway, this is a constant, right? So if we use this reciprocal, free electron mass and this constant, so these are just constants. So we just capture this. So we know that here, right? And then if E is in unit of EV, and then if you capture this density of states, you get this number. So E, the number is 1 electron volt, and the whole thing will be 1. The 2 electron volt, the whole thing will be 2. And then if you calculate density of states, so this number, and then per unit volume in real space, and then, sorry, this is per unit volume in real space, and then this per unit energy interval, in reciprocal space. Sorry, that's a typo here, okay? So this should be, this whole thing should be per unit energy interval. So it means energy is EV instead of V. V is watt. Okay? So EV is energy. So this means that if you substitute energy in EV into this equation, and you calculate this number, and then your density of states basically be this number in unit of per unit energy interval in energy space, and then per unit volume in real space, right? So from here you can see that if E is 0, this means if you look at the Fermi surface, and the Fermi surface basically E will be EF, right? So if EF, so if your Fermi surface is very large, a Fermi sphere is very large, and then EF will be very large, and then you have large density of states. So this is understandable because on the Fermi surface, your energy is the same, right? So this means that when energy changes a very small amount, and then total number of K states will change a very large amount. This means that total number of electrons will change by a very large amount. And so, so inside Fermi C, of course, your energy is small. This means if you have a equal energy surface here, you have a very small spherical surface here, and then the number of electrons occupy this small surface, of course, will be very small, and then density of state very small. So this means that density of states for free electron is always largest at the Fermi surface, right? We can actually calculate the Fermi energy of free electrons. And so this is the Fermi energy, right? So now, and then so this is just the electron density. So we substitute in here, and then H and then 2m this constants. So we substitute in, and then we find that this Fermi energy is given by this one. So and m again is a effective electron mass, and does not have any dimension. All right, it's dimensionless, and then n is a carrier electron density. If you know this, and you should find out what's the Fermi energy. Okay, and the Fermi velocity. This means electron at the Fermi surface we have this velocity, and then because it's a momentum. So momentum is hk divided by mass, and then given by this. Again, this is the effective mass. So once you know electron density, you can find out we have basically Fermi velocity. And for that, for copper, and this is EF, if you substitute copper electron density, this is what we already gave in the previous slide. And then you find that this electron energy is 7 eV. So it means that the Fermi energy of copper is very, very high. If you convert this into temperature, so into a thermal temperature, something like a, so how to do this? So we just do this very simple calculation. So that means just EF equals KBT, and KB is Boltzmann constant, and then so this will be energy, so temperature called electron temperature. If you calculate this, you can see that this is huge. So this is what I mentioned in a second lecture when I talk about the temperature. So the normal temperature, basically the temperature of a lattice temperature. And then of course it cannot be as high as this, for example, at room temperature, and the lattice temperature basically room temperature, right? And you have a piece of copper, you can use your hand to touch, right? It's a room temperature. And however, if you really use this kind of equivalent concept to calculate this electron temperature, you can see that it's very high. So it means that electron is very hot inside the metal. So that's the reason why electrons are moving at a very fast speed in the metal, right? For example, electron on the Fermi surface, you can see that this is the speed. It's very high. So electrons basically should have a picture that electrons are very, very hot in metal, and also they're moving very fast inside the metal. However, they are moving in all different directions. So that's the reason why there's no net current flowing. So in reciprocal surface, it's very easy to understand. So because for every K state, so it's for example, so you have one K state at this point, and another one which is one here, the K is just opposite. So that's why they cancel out each other. And then you have another one here, and then there's another one here. So since it's spherical, so that's why eventually the net current is always 0. Okay. So next, look at the density of states in 2D case. This is quantum well. So now, suppose electron now is quantized in x direction, confined in x direction. So electron can only move in zy direction, right? In this case, and then so each state in 2D case can be occupied, of course, by 2 electrons, right? And then the area occupied by 1 electron in K space, in 2D K space. For 2D K space, of course, you don't have a spherical shape, right? So you only have this kind of a circular disk, right? Because you only have so K parallel. So basically, it's a KZ and KY. Okay. So 1 K state, 1 electron, sorry. So 1 electron in K space will occupy this area, right? And then since your the Fermi surface space is a Fermi disk, and then the total area of the Fermi disk, of course, is given by pi, this is pi K parallel square, right? So so now, if we don't look at the Fermi disk, we just look at a small disk inside this Fermi disk, basically this region, right? And then if this radius is given by K parallel, and then we can calculate the area of this disk is pi K parallel square. So that is this one. And so this is divided by the area occupied by 1 electron, that's this one. And then you get total number of electrons in reciprocal space, right? 2-dimensional reciprocal space. So because your real lattice is also two-dimensional. So real space is also two-dimensional. So this is what you have. Then we can convert this one to energy, right? Because we have this, okay? So we convert to energy, we just look at the single energy level first. Okay, so this is the energy which is given by this, and then we get n as a function of E parallel, okay? So we differentiate this one from both sides with respect to energy, and then differentiate this one from both sides with respect to energy, and then bring this one over, and then we get the density of states for single energy band. Remember, for 2D case, we have multiple energy bands, right? For single energy band, so then we have this dn is the number of electrons per unit area in real space, and then per energy interval in energy space. So this basically is the density of states in K space for 2D system. And then that's given by m divided by pi h squared. Okay, m divided by pi h squared. So unlike in 3D case, you have energy root square E. We don't have, this is just a constant. M is constant, h is constant. But this is only for one single energy level. And then we have multiple energy levels. So what we do that we just need to multiply this one by this step function, right? Step function. This means that every time and when this, so the reference is the median energy level. So it means that you look at it from each median energy level. So once this is greater than 1, and then so this will be 1, below that will be 0. So eventually you can sum all of this for different energy levels, right? That's the basic concept. So this will be the total density of states for electrons in 2D system. And of course, it's very unique. You get step function, and then but it's not increasing continuously with respect to energy. In this for 2D case. Next, we look at the 1D. So 1D case, so you can see that in real space, the electron can only move in one direction. Here we use y. Okay. So of course, the reciprocal space is also 1D, and then one electron in this 1D space will occupy this small interval. So that interval basically is 2 pi or L, right? And then we look at the small interval, small 1D interval in the K space. Basically, it's from here to here. So this is Ky, and then from here to here will be 2Ky, right? So within this 2Ky region, so number of electrons occupied by this region, so the number of electrons in this region will be 2Ky divided by 1 over 2 pi over L, right? So that eventually is given by this. So 2Ky divided by the interval occupied by 1 electron. Okay. So, and then in this case, and you get total number of electrons which occupy this region in 1D case, right? Again, this Ky is related to energy by this relation. Again, we just look at, if we look at each energy subband, and then we count this energy from the edge of the band, and then we don't have this, right? This is a reference. It's a reference, the minimum energy level for each subband. So if we catch energy from each subband, and then we don't have this, and then we simply have this, right? And then we substitute this in. We substitute this in to this here, and then we get n as a function of Ey, right? And then we differentiate this one from both sides with respect to n, and then we rearrange it. Then we get a number of electrons per unit length in real space, and then per energy interval, per unit energy interval in energy space. So that basically is the density of states for 1D system, which is given by this. So in this case, you can see that it's 1 over root square Ey. Remember, Ey is calculated from the edge of each sub-energy level. So if you have a multiple energy levels, so total density of states is given by this one. Again, we have this step function. So, but this energy is captured from the edge of each subband. So they're basically total quantization of x-axis and then also z-axis. On the y is free to move, right? So, so here also you have to capture from here, and then you sum all of this, and you get a total density of states at energy E for 1D system. Okay. If you plot all this together, that's what I have. So this is the energy. Okay, this is energy, total energy. Okay, and then this is the density of states. And then for 3D case, we have this kind of parabolation because density of states is proportional to rho square E, right? And then for 2D case, and then we have the step function. So it means that this is a density of states for the first energy level, is the second energy level, and the third energy level. And so for each energy level, and then density of states is a constant. So we just go back to look at this again. So that basically is this one, which is a constant, right? Constant. And then when you jump by one energy level, and then increase by one. So that's why it's like this. Okay. And then for 1D case, again, due to quantization, you have multiple energy levels. And then at each energy level, you have this sharp jump. So why is it sharp? That because that, is given by this one. So it means that every time, theoretically, this will go to infinity. But in actual case, due to broadening of energy levels, this will never go to infinity, right? But this will be very large because at the edge, so that's a reference of the edge. So at each edge, so this will approach to zero. So that's the reason why you have this large spikes. Then, so after that, of course, this baseline will increase. That because that, for each step, you just sum up, right? So eventually you have this, right? And then this is density of states. So as I explained previously, this 2D density of states is extremely useful. You know why? Because the density of states is a constant at a certain energy level. So for example, if you fill up your two-dimensional K states, and then up to here, and then you stop it. So this will be a Fermi level, right? So use up all the electrons. And then you can see that surrounding this Fermi level, the density of states is a constant. So this means that when your temperature change a little bit, when temperature is fluctuating, right? And this, the distribution, the population of electrons will not change so much. So this means that it will make your system very stable, right? And also, if you compare to this 3D case, and then you can see that your density of states can be much smaller, right, depending on where you are. And then, so this is the case. Sometimes, for example, you want to make a semiconductor laser, and then this property is very good because you don't need so much electrons in order to achieve this so-called population inversion, right? So in other words, the threshold for you to turn on the electron will be small. So this means that the electron will be the laser will not generate so much heat, right? So then anyway, I will not go to details, so that you have many interesting properties for 2D systems. And 1D, as I explained, that is not very stable. So remember, and this spikes is supposed to go to infinity, right? So that's why if you have a very large, very sharp spikes at the Fermi level, and so if your Fermi level somehow end up near this region, and then your system is bound to be unstable, right? So that's why you may observe some interesting physical phenomena, but it's not very good for practical applications. Okay, once you know this, and you know the density of states, right? So we know that electron will fill up the energy space or K space from the smallest energy, and eventually you end up at the Fermi surface. So at the zero temperature, your Fermi surface basically is supposed to be very sharp. So any states below Fermi level will be filled up by electrons, but any states above Fermi level will be empty. But at the finite temperature, this is not the case. So electrons are always jumping back and forth near the Fermi level. And so, of course, eventually you reach an equilibrium state, but it's a dynamic, some sort of dynamic equilibrium state. This means the electrons are not actually stationary at the Fermi surface, are moving. But there's statistically, you can have some sort of a statistical model to calculate distribution, probability of electron at a certain energy level near the Fermi surface. That's called Fermi-Dirac distribution. So the Fermi-Dirac distribution, okay, this is already explained. I mean, at the T equals 0, so the Fermi C is completely filled up. And then, so those above the Fermi surface, there's no electrons, that empty, right? And then, as I said, that we are only interested in electrons near the Fermi surface, and because they determine the property of the electrons inside the solids. However, without electrons at the deep of Fermi C, and then you won't have electrons at Fermi surface as well, right? So that's why all the electrons at Fermi C are still very, very important. And at the final temperature, you can see that the probability for electron to occupy the states below the Fermi surface is not unity, not 1. And then the probability above Fermi surface is not 0 either, right? So, and they actually certify this Fermi-Dirac distribution. And anyway, this is based on quantum mechanics, and because electrons are fermion, right? So fermion are half integer spin particles, and then they occupy this Pauli exclusion principle. So this means that you cannot have more than two electrons occupy the same K state, right? And so you have two because you have a spin degeneracy. Okay, so if you consider the electron state anyway, if you is K resolved, and then you can also see that a single quantum state can only be occupied by a single electron. Anyway, right? And then when you fill up this K space, you always fill up from the smallest energy first, right? Eventually, after you use up all the electrons, you stop there. That basically a Fermi surface, right? And at 0 temperature, this is already explained. I will just jump. So now the distribution basically is in here. So the probability for you, the probability for electron to occupy a certain energy level, right, at a certain temperature is given by this Fermi-Dirac distribution. Okay, so it's given by 1 over 1 plus this exponential term. So obviously you can see that if this term is 0, and then the probability is 1. So this 0 means that when t approaches 0. Okay, so when t approaches 0, and then this is this E minus EF is negative. So when this is negative, this means that E is more than EF, and t approaches 0, and this whole term will approach 0, and then you get this one 1. And however, when t approaches 0, if E is greater than EF, and then this will approach infinity, and then eventually this will be 0. So this means that you have a very well-defined, very sharp Fermi surface, right? And then all other temperature, and then this will be finite. So it means that this will be a positive number, and then eventually this is more than 1. Okay? So, so now if you look at the distribution, and so this is what you have, and so now this is the distribution function Fe, and then this is the energy, right? And then this is the Fermi level. So you can see that when temperature is low, say 500 Kelvin, is considered quite high, but you can see that the distribution is pretty much below the Fermi C. You can see that it's 100%, right? It's unity. And then when you approach the Fermi surface around here, you can see that this F will be smaller than 1. And then above Fermi surface, you can see that it's not 0, right? You have a finite value for this distribution function. So when you increase the temperature, of course, this distribution becomes more rounded, right? You have more electrons above Fermi surface, and they have more vacancies below the Fermi surface. Okay. Now, so this is a zoom up of this region. So roughly you can see that okay, this is a Fermi surface, right? And this is Fermi surface. So this is energy, and then this is the F. Okay, it's different from this one. So this is F, this is energy. So now, so you can see that when energy near the EF, and you can see this you have this kind of a smooth distribution, right? And so this overall curve is given by this Fermi-Dirac distribution. And however, when this E is much larger than EF, for example, about 3 KT is the thermal energy from EF, and then roughly you can see that since this term is much larger than 1, and then just ignore this 1, you get this. This is a Boltzmann distribution. Right? It means that far away from thermal surface, you have Boltzmann distribution. Okay? And then far below this, the 1 minus this 1. So this basically, so this means that you have empty states right below the thermal surface, right? So this is the very important concept. So now, so once you have this, and then in next lecture, we'll talk about electronic band structure. This means that under water condition you have a semiconductor, and under water condition you have a metal. And so this Fermi-Dirac distribution and also density of states, and we'll only use it in lecture 5 when we talk about carrier distribution in the semiconductor, right? So so that's all about this lecture 4. Then we'll stop here, and then we'll continue. Sorry, this is lecture 3. In lecture 4, we'll focus on electronic band structures of real materials.